Good morning. Happy first rain of the day, and also, boo. That was exciting. You know what will not be exciting is the topic of today's class. But in order to make it more exciting, I'm going to talk like this, with a lot of gesticulating and stories, and it'll be fun. Okay, so get this. We're going to take all the Van der Waals forces, all the dipole, 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 induced dipole, and dispersion forces, and ball them all up into just something called the Van der Waals force. Then we're going to take two objects. It could be a molecule and a surface. It could be a sphere and a flat surface, or it could be two flat surfaces. In fact, we will explore them all. And we'll add up the Van der Waals interaction of that molecule with every other molecule in that surface. Then we'll take the sphere in the flat surface, and we'll take every molecule in the sphere and add up the Van der Waals interaction with every molecule in the flat surface. And then for the two flat surfaces, we'll do the same thing. Interparticle forces. This is chapter 11, bankruptcy. This is chapter 11 in your book. Chapter 12 we're not going to cover. Chapter 13 is largely a reprise of chapter 11, except we take all the balled up Van der Waals forces and all of the constants that will come out of our derivations, and then we're going to encapsulate all of that stuff into a parameter called capital A, the Hamaker constant, which conveniently you can look up in a table. Okay, so recall that little w is now big W when we're talking about surfaces, and the center-to-center distances between the molecules, little r, we're not going to use anymore. We're going to talk about the distance between the surfaces, and that will be big D. If we use a big R, we're talking about the radius of a particle or the radius of curvature of that particle, or say some other object. Say it's a cone, we'll talk about the radius of curvature. Turns out that the stuff up here on the cone doesn't matter so much. It's really in the material that's closest to the interaction. Okay, so consider a molecule d away from a surface of like molecules. We're going to assume intermolecular pair potentials of the form we're used to, W of R equals minus C over R to the N, and that additivity applies. What do I mean by additivity? That each one of the interactions is pairwise additive. We're going to forget about all the multi-body effects that we talked about a little bit in the chapter on Van der Waals and on dispersion forces. And it turns out if we ignore those effects, we'll get pretty much the right answer. So that's okay. So our coordinate system looks thusly. Here is our molecule. This is our z-axis. This is our x-axis. All of this stuff on the other side of the x-axis is a solid material, or it's a condensed phase that is some distance d away from this molecule. So this distance is d, and we'll call this point z equals d. And we could, in principle, integrate the interaction between this molecule and every molecule like it in this surface in a number of ways, but the way that your book does it, and the typical way of doing it, is to imagine that you are integrating with a disk, and you're going to integrate disks as you dig in further into the material. And the disks have the following dimensions. They have a square cross-section with cross-sectional area dz times dx. And I'm going to try to render a 3D structure here, and it looks like crap, like it has every year for 6 years in a row. And the same thing in the back. It's kind of like a wheel with a square cross section. Okay, this distance is x to the x-axis, this line segment here. This is the cross section of the ring, and this is a surface of like molecules. The ring has a volume of 2 pi x dx dz, where this is the circumference and the dx dz is the cross section. And the number of molecules in the disk is equal to the number density times the volume. So rho times 2 pi x dx dz. And this is the density in units of molecules per volume. So what's the net interaction energy? We're going to set up an integral over x and z. Net interaction energy W of d of minus c over r to the n rho 2 pi x dx dz, which simplifies to minus 2 pi c rho from z equals d to z equals infinity over the dz's times the integral over the x's from 0 to x equals infinity of x dx I'm going to write something here. I forgot to write something up. I forgot to write an important piece of the geometry. Over z squared plus x squared to the n over 2. Where did that come from? Came from the Pythagorean theorem, because the distance from the molecule to, does everyone have this? I'll put it back up in a second. The distance from the molecule to the cross-sectional element is z squared plus x squared under the square root. Okay, you can solve this integral in whichever way you want, and you get 2 pi c rho over n minus 2 from z equals d to infinity of dz over z to the n minus 2 equals minus 2 pi c rho over n minus 2 times n minus 3 d to the n minus 3 for n values greater than 3. If we're talking about the Van der Waals force, which we almost always are, we can substitute n equals 6 and get minus pi c rho over 6d cubed for n equals 6, and that is the Van der Waals force. So remember, for the intermolecular part of the course, we had all of these different interaction potentials. So permanent dipole interacting with permanent dipole, dipole interacting with uncharged molecule, an ion interacting with an uncharged molecule, and we ended up with all of these equations for something over r to the whatever, usually r to the 6th if it was a Van der Waals force. So what we're going to find is that there will be, in chapter 13, there will be a table that has forms like this, and you'll have this table on any of the exams. You'll have a table with formula like this that have something about the material, so it's Van der Waals constant times its density and some factor of d, the distance between the particles, raised to some power. And that's the form that we'll see in all of these examples. Okay, how about a sphere and a surface? A planar or a flat surface. Could at least try to draw a line horizontal. Okay, so now what we have is a sphere with radius capital R, which is distance d away from a a flat surface of like molecules. This point we'll define as z equals 0. And what we're going to do is take disks of the sphere with thickness dz, where the chord of this disk is x. I guess the chord would be 2x. The center point we'll call z equals r. The end point we'll call z equals 2r. This distance is zd plus z. And this is a thin circular section. So we're going to skip to the end. So for close-ranged interactions where d is less than r, we have w of d equals minus pi squared c rho squared r over 6d. And for long range, we have w of d equals minus pi c rho times 4/3 pi r cubed rho over 6d cubed. So we should notice a similarity between this formula and that one over there. So this is really for a sphere that's a little farther away. What we're really doing is taking the number of molecules in the sphere and multiplying it by the molecule surface interaction. Which is kind of what we would expect. If we bring the molecule farther away from or bring the sphere farther away from the surface, then we just have some number of molecules in the sphere interacting with every molecule in the surface. And this part of the equation is just the molecule surface interaction. In this formula, only the molecules near the surface of the sphere, dominate the interaction. That's basically what it's telling you. Yeah.
For the close end, should it be 6d cubed?
Just d. I'm not going to derive it. We'll be here for another hour. rather than hand wave, sorry, it's just too much detail. How about a surface-surface interaction where they're both flat? And this is best thought of as a unit surface. So this is a unit area, like 1 square meter. And we have Z equals 0, Z equals D. We have our infinitesimal region with units, or sorry, with thickness dz, which is distance z from the surface. And if you want the derivation, it's on page 211. Where again, each point in the unit surface interacts with rings in the flat surface. But there's essentially no intermolecular forces involved in the derivation, so we're not going to do it. But it's the same, we're just building up. We're just building up. Okay, so the final result is W of D equals minus pi c rho squared over 12d squared, and this gives you an energy per unit area. Okay, as we graduate from intermolecular forces to intersurface forces, we really need to change the way we think about interaction strengths from energies to force, or from energies to forces. In intermolecular forces, we were always talking about, let me rephrase. In intermolecular interactions, we were always talking about them in terms of energies, kTs, kilojoules per mole, all that stuff. Because energies are what you get when you measure something calorimetrically, for example. Thermodynamic data are always in energies. So thermodynamic data are always in energies. You can do a calorimetry experiment and get the delta H of some interaction. You can heat something up, and you can know the number of joules that you put in. You can know how many joules you had to put in if you have boiling pasta water and you fall asleep and it all evaporates. You know how much energy had to go in there. But we never care in our daily or even scientific lives that much about how many newtons were involved in the interactions, how much force we had to put into the system. Although I think those are good numbers to know, particularly in nanoengineering, that a covalent bond is something like single nanonewtons. A Van der Waals bond is something like 100 times less than that. A really strong Van der Waals bond between large molecules might be 10 times less than that. But in intersurface forces or in interparticle forces, the force itself, the actual force, is what is important because you can actually measure it. I mean, if you have an AFM tip, atomic force microscope, you can actually measure the force between the AFM tip and the surface in some number of newtons. Suppose you have some adhesive tape on a wall. It's a macroscopic object, but the interactions are mediated on a nanoscale distance. We actually care about how much force some adhesive produces. Suppose in a civil engineering project you have to engineer a new type of thermosetting epoxy, and we care about the force. We don't care about the energy. I mean, we do care about the energy, but when the rubber meets the road, you care about pounds force and all of that other non-MKS units that are used in the real world. So we're talking about, you know, how much weight can this thing produce. We're not going to take a bridge and put it in a calorimeter. So conveniently, force and energy are intimately related here. So I'm going to make a very general statement in intermolecular forces, but interactions, because I need to use the word force for another meaning. Intermolecular interactions. Energy is easier to measure in interparticle or surface forces. That's horrible. In interparticle and intersurface forces, force. Not only easier to measure, but also probably more important too. I mean, if you know that the particles in a colloidal suspension have a net negative interaction potential, that's not very good for your suspension, right? Because they'll precipitate. So conveniently, recall that for a sphere plane interaction, we had W of D equals minus pi squared C rho squared R over 6D. We didn't have to recall very far because it's out there. Then the force for a sphere plane interaction is minus dW of D over dd equals minus pi squared C rho squared R over 6D squared. Now there's a relationship between the force and the energy of a factor of 2 pi of a factor of 2 pi R. What we have is the force between a sphere and a plane is a factor of 2 pi R times WD of 2 planes. So what we're doing, this is our 2 planes. So this relationship here, if you know what the interaction energy is between 2 planes, which is easier to calculate, and it turns out that the force between a sphere and a plane is easier to measure. Then you should be able to switch back and forth between the energy between 2 flat surfaces and the force between a round object and a flat surface. Why is it hard to measure the force between 2 flat objects? Because at the distances that are relevant, so a few nanometers, tens of nanometers max, it's really hard to make 2 flat surfaces exactly flat with each other. So it's really hard to measure the force even between 2 polished surfaces of a silicon wafer. If you put them together, you're not going to get an accurate force. We'll find out in next class that the adhesive pressure between 2 truly flat surfaces is enormous, even just by Van der Waals force. Like we're talking thousands of atmospheres. So, you can think about this. Think of your favorite Van der Waals substance. Like, it's Halloween, so like a Jolly Rancher. And imagine if you had pliers on both sides of the Jolly Rancher, which is just a Van der Waals solid, how hard you would have to pull to pull it apart. Van der Waals bonds are strong. Strong with the force. It turns out that this relationship here is remarkably valid. So while is remarkably general. So while we validated it for Van der Waals forces, it actually doesn't matter what force. If you have the force, it could be a Coulombic force, it could be an electric double layer force, it could be a Jedi force or a Sith force. So this is valid for any force law, not just Van der Waals. So a Russian scientist by the name of Derjaguin figured this out, and what he wanted to do was generalize these energy laws so that you could convert between geometries. So is there a general form of this where you have some flat object and some sphere, some big sphere and a little sphere, 2 big spheres, 2 little spheres, where you could use this this generalization in a slightly more general way. Okay, horrible preamble, but we're trying to be exciting here. Okay, so what is my personal history with Derjaguin, this Russian scientist from 100 years ago or so? Okay, well, it was less than that. Anyway, 5 years ago, I was at a holiday party for my wife's then boss, Christmas party, even though he was Jewish, which is fine. And they had tequila shots, and he said, let me show you how it is we drink tequila. And so after like 3 or 4 shots, I asked him what his, or he asked me what I taught. I said intermolecular and surface forces. And I said, what did you study in your PhD? And he said, I studied intermolecular and surface forces. And this was at Moscow University or something. And he said, and I said, oh, so you must know the Derjaguin approximation, because I just taught it in class yesterday. And he said, Derjaguin was on my thesis committee. Fascinating. Okay, where do I want to start? Does everybody have, I think I can do this. I think I can do this in 3 boards. Strap in. This is the Derjaguin approximation. The derivation in your book is not as good as the derivation on Berg, which is on reserve in the library, page 544. But I'm going to try to do as good a job as Berg did. Okay, so imagine that we have 2 spheres interacting, and they have 2 different radii. And we are going to divide these spheres into these annular disks, so that depending on your sci-fi and television proclivities, could either be the Death Star or the Technodrome from Teenage Mutant Ninja Turtles. And this sphere has radius r1. And on the other side, we have something. I'm going to draw it roughly the same size, but it need not be the same size. And this sphere has radius r2. The surface to surface distance is d. The axis along which we are going to integrate the forces is z. The thickness, I'm sorry, yeah, I guess you could call this the width, let's say the width of these annular disks is dx, not dz, is dx. The distance, the radii of these annular disks is x. In fact, all of these distances are dx, and there'll be dx on this side as well. The annular disks have area of 2 pi x dx. If this looks like a big dx, it is. This is supposed to be infinitesimally thin, but there it is. Limitations of my artistic skills. And we are considering the interaction for large radii, and I'm going to add of curvature, because this works just as well if these are spheres or if they're two cones that come together with roughly spherical tips, or AFM tips on a surface. It will also work in that case. So the R's are radii here for spheres, but they could really be radii of curvature. Okay, so we have large radii of curvature relative to separation. D less than R1 or R2. How much less than? Factor of 10-ish. So what we want to do is integrate the infinitesimal contributions of force between the curved objects in terms of the force between opposing disks. Let me write that down. So we want to integrate the infinitesimal contributions to the force between the curved objects in terms of the forces between the flat disks. We don't care what the origin of the force is. Again, Van der Waals, Jedi, Sith, doesn't matter. Could be anything. It doesn't matter where the force arose from. It doesn't matter that the force here in the case of Van der Waals force actually arose from lots of molecules behind it. It doesn't matter. We're just considering some generic force emanating from the surface of these flat disks. So we need an expression to integrate. So we want to integrate the differential forces between curved objects in terms of the force law as a function of z of the disks times the area of the disks. This is the normal force per unit area. So we need to integrate with respect to z. So our goal is to replace the x's with z's. And we'll use a couple of trigonometric arguments to do this. So if you look at these disks in a two-dimensional cross-section, where we have this area, this distance as dx, and the center to center, the axis running through the center to center distance is the z-axis. The intersurface is d. The radius of the disk is x. And we're going to call these little line segments here Z1 and Z2. You don't have to derive this on an exam or the homework. I just want you to know where it came from because it's like one of the central nuggets of wisdom is the generality between force and energy and interparticle forces. So anyway, so we can say just by arithmetic that z is equal to d plus z1 plus z2. And by the Pythagorean theorem, we have r1 squared equals r1 minus z1 squared plus x squared equals r1 squared minus 2r1 z1 plus z1 squared plus x2. Z1 squared, Derjaguin said, was small enough that we can ignore. That's convenient. I love when they do that in derivations. I never would have thought of that, but that's why some of these people have Nobel Prizes. R1 squared minus 2 R1 Z1 plus X2. I don't think Derjaguin does, incidentally, but anyway. That's how you have equations named after you, because you know what parts of the derivation you can ignore and what parts you can count twice, Van der Waals. And by something from 10th grade math called the Chord Theorem. Says that, anyone remember what the Chord Theorem says from high school? I don't think anyone learned it since high school, because who cares? It says that if you have two intersecting chords in a circle, a chord is like a diameter, but it can be anywhere in the circle. You can have a chord that's small at the edge of the circle to equaling the diameter in the middle of the circle, and then you can have it anywhere you want. Two intersecting chords, the line segments, the products of the line segments that on either side of the intersection point are equal. That's the Chord Theorem. Derjaguin knew the Chord Theorem. And that said that x squared was roughly equal to 2r1 z1 equals 2r2 d2, just kidding, 2r2 z2. I was on a late night flight last night and I watched Star Wars on my computer, so there it is. Which one? The Force Awakens, because I'm getting ready for episode 8. Z1 equals x squared over 2 R1. Z2 equals x squared over 2 R2. Almost done. We can now write Z as equal to D plus x squared over 2 times 1 over R1 plus 1 over R2. If we differentiate this, dz dx, but I'm automatically going to put the dx on the other side, we have dz is equal to 1 over R1 plus 1 over R2 times x dx. And we are going to use the substitution that x dx is equal to 1 over R1 plus 1 over R2 to the minus 1 dz. To achieve the expression df of z of the curved surfaces equals f of z of the flat disks into which we've divided it times 2 pi 1 over R1 plus 1 over R2 to the minus 1 times dz. Or, what am I? I'm making propitiations to Derjaguin's approximation. F of z curved equals 2 pi R1 R2 over R1 plus R2, which is equivalent to this inverse addition of two fractions. By some law you probably learned even earlier than the Chord Theorem, times the integral from d to infinity of f of z of the disks dz equals the final answer 2 pi times R1 R2 over R1 plus R2 times, what's the integral of f of z of the disks dz? Is the energy between two planes per unit area. I've used really low value real estate for the most important result here. I'm sorry. This is 2 pi times R1 R2 over R1 plus R2 times the energy WD of the planes. This is the Derjaguin approximation. And what are some of its consequences? Notice that this up here looks like a special case of this down here. Let me write it up here again. F of z of curved objects equals two pi times R1, R2 over R1 plus R2 times the energy that one would calculate between planes of the same media. This works for any force law, whether it's attractive, repulsive, oscillatory, so long as the separation d is significantly smaller than the radii, R1 and R2. And in every case we'll be dealing with in this class, that condition will hold. So what are some consequences? First consequence, if R2 is much greater than R1, the Derjaguin approximation reduces to sphere surface interaction, which we had before. F of d for spheres equals 2 pi R1 WD planes, which is just what we had before. And why wouldn't it? If one sphere is this giant-ass thing, and then this other sphere is tiny, then it will see the second sphere as a flat surface. For two equal spheres, R1 equals R2 equals R, then it reduces to F of d spheres equals pi r times WD between planes. And for spheres in contact, W at the hard sphere diameter of the molecules that make up the sphere. We call this minus 2 times the surface energy per unit area. And we can say that the force at contact is the force of adhesion equals minus 4 pi gamma R1 R2 over R1 plus R2. And for some reason, the last topic in this chapter has nothing to do with the rest of the chapter, but we're going to mention it now. And those are area to volume effects. This is kind of the key to nanoengineering, right? The key to nanoparticles is that the since if you have a small particle, as the particle gets smaller, a larger and larger fraction of its atoms are at the surface. Now we know from the first part of the course that surface atoms have unfilled valencies around them. So as you get smaller and smaller and smaller, the molecules, all of the molecules in your object actually have properties that are more like surface molecules. So a very small object, which is mostly surface, has properties that are quite different from the bulk. So you may know about the absorption of quantum dots, for example, how they're size dependent. Those are quantum effects. But there are also properties that properties related to thermal and mechanical properties that are also related to these skin depth effects. Some properties don't reach bulk values until skin depth, which we use the Greek letter lambda. Skin depth is surpassed. Because, for example, the bulk cohesive energy of a molecule is not saturated if it's near the surface because it doesn't have all of its friends around. So cohesive energy this is latent. This effect is called latent heat depression. And the latent heat depression is U of R equals U bulk over 1 minus lambda over R, where R is some characteristic size of the particle, like a film thickness, or a radius. And in this case, to see a latent heat depression, your skin depth, depending on the material, is something like 0.3 to 2 nanometers. Surface tension is also affected. So, for example, if you have a really thin film of molecules, the energy required to have a molecule go from the surface to the bulk, well, you're starting out in the bulk at being pretty close to the surface anyway. So you're already kind of high in potential energy. So it's not that much of a stretch to stretch the film out and have the molecule go to the surface. So surface tension as a function of R is the bulk surface tension over 1 plus the skin depth over R. And the skin depth for liquids could be something like 0.3 to 5 nanometers, depending on the material, depending on the media, and how far away from its center its intermolecular forces go into the bulk, and a melting point depression. Melting point depression, so T as a function of R, is melting point of the bulk times this factor 1 minus lambda over r for lambda equals 1 to 3 nanometers. So the effect here and how it originates is more important than what exactly lambda is for a given system. So these are surface to volume effects that deal with thermomechanical properties. If you ever have a nanowire, for example, silver nanowires are often used as transparent electrodes in research. In fact, some of these types of structures are actually being commercialized for smartphone and TV screens and solar cells. And there was a paper a few years ago about irradiating them with just light. And because you created these surface plasmons in the nanowires that resonated at the frequencies you were irradiating them with, they heated up. Not hot enough to melt bulk silver, but hot enough to melt silver nanowires because of melting point depression, and they welded to form a much more conductive network. So the surface tension of a very thin film is obviously going to be lower, and cohesive energy density goes down for pretty much the same reason that the melting point also goes down. Okay, so the main points today were thinking about how you use these pairwise additive interactions to get the energies and therefore the forces between nanoparticles up through macroscopic objects. So these laws actually correspond to not just colloidal suspensions, but really really objects in the real world. Are the force between our finger and our palm or whatever in real life. So we're going to develop this a little bit more with several examples on Thursday, and we will start with taking all of these factors of pi and rho and c squared, and we're going to ball them up into something called the Hammacher constant, which is a lot easier to deal with. It's a little bit like the Van der Waals coefficient, but it's for nanoparticles and macroscopic objects as opposed to molecules. Thank you for bearing with me during this geometry-infused lecture, and we'll see you on Thursday.